Okay, as you know, I'm not at school today. Trust me, I'd rather be there with you. Not feeling great, but I'm going to try and knock this one out, at least to get you a fighting chance to understand these sums before we get to the good stuff. So we've been adding up a few rectangles to estimate the area under a curve. But in order to zero in on the exact area under a curve, we really need to get serious about finite sums. And to do that, we need a more formal notation. So we're going to use the sigma notation, which you may or may not have encountered in your previous math classes, to help us formalize that process. So here's my best shot with a stuffy nose at explaining that to you. So the Greek letter sigma, which is a capital sigma, corresponding to our letter S, stands for sum. The index of summation usually is indicated by the letter K, and that tells us where the sum begins. It's below the sigma symbol, and then where it ends is indicated above the sigma symbol. And then next to the sigma is our A sub K, which is a formula for the kth term in our sum. So if we were going to expand this sum to show what it means is we start counting with k equal 1, and then we keep going 1, 2, 3, 4, using our natural numbers until we get to n. So this sum would be written out in the long way as A1 plus A2 plus A3 plus A4. Now, we don't really know what n is, so I'm just going to use the old ellipses here, which is 3 dots, meaning the pattern continues, and eventually we get to A sub n. And this notation, this sigma notation, is a concise way to write out this sum. And in terms of what we've been doing, each one of these A's is like one of our rectangles, right? So it's been okay when you want to add up, 4 or 5 rectangles, you just write out the sum and add them up and get the answer. But as we mentioned in class, we're going to want to send the number of rectangles to infinity. And to do that, we're going to need to use this formal notation so that we can take the limit as n goes to infinity. No limits today. Today we're going to practice the notation, but that's what's coming, as I mentioned in class the other day. Okay, so today my goal is just to get you computing some sums, understanding what the notation means, and getting some quick answers. Let's see if I can explain that before I fall back asleep. So I stole this table out of our textbook, and I just wanted to show you that for different sigma notations, the way we expand it is written out in the middle here. So, for example, this sigma here for k equals 1 to 5, what this means is start by putting 1 in for k, and that answers 1. Then put a 2 in for k, then put a 3 in for k, then put a 4 in for k, and then put a 5 in, and 5 is where we stop, so that's our last term, and then we add up this series. 1 plus 2 plus 3 plus 4 plus 5 is 15. That's how the notation works. It's not rocket science. It's just a way to indicate. I'm just erasing this so I can do the next one. It's just a way to indicate that we're going to add up those numbers according to this formula, which is just k. So this formula here is more complicated, but the process is the same. Our first iteration, our a sub 1, is going to be calculated when we put a 1 in for both of these k's. So negative 1 raised to the first power times 1. Next time we're going to put a 2 in for both these k's. Negative 1 raised to the second power times 2, and then we stop at 3. Negative 1 raised to the third power times 3. So this works out to be negative 1 plus 2 plus negative 3, which the answer is negative 2. Remember, our goal is to get a sum, which is the answer to the addition problem. So these are our sums here, 15 and negative 2. And the formulas could, get more complicated. Here's a complex fraction, or actually this isn't a complex fraction, but it is a rational expression. Let me just erase this so that it's out of your way. this one right here, we're going to stick 1 in for both of the k's. That's 1 over 1 plus 1. And then we stop when we get to 2, so we do 2 over 2 plus 2. 2 plus 1, excuse me. And that works out to be 1/2 plus 2/3, which is 7/6. So the sum of that sigma notation is 7 over 6. Same thing with this one. K squared over k minus 1. We're starting at 4 this time, and we're ending at 5. So the first time we stick 4 in where k is, that's 16 over 3. And the second time we stick 5 in where k is, that's 25 over 4. And when you add those up, you get 139 over 12. This chart is just showing you different examples of how we expand and then add up the sum. Okay, hopefully you're getting the hang of this. Let's see if I can have you practice a couple. When you get to the assignment, the first thing you're just going to be asked to do is rewrite each series as a sum. In other words, you just want to write out what the sum is. You don't have to get the answer. You can if you want, but that's not my goal here. My goal is to expand this sigma notation. So for example, in number 1 here, I'm going to start at 1 and stop at 4. And I just have to fill in the m times m plus 2. So when m is 1, that's 1 times 1 plus 2, which is 3. So 1 times 3. The next time I have 2, and 2 plus 2 is 4, so that's 2 times 4. The next time I have 3, and then 3 plus 2 is 5. And then I end at 4, and 4 plus 2 is 6. So this expansion is just 3 plus 8 plus 15 plus 24. This is the answer that I'm looking for. If you want to go ahead and add it up because it's driving you crazy, go ahead and do that. But I'm not going to worry about that part when I say rewrite the series as a sum. Similarly, with number 7 here, we do the same thing. We're going to start at 3 this time, so just be careful. Notice where you're starting. And the formula this time is going to be 500 minus m squared. So 500 minus 9, that's 491. And then 500 minus 16 is 484. And 500 minus 25 is 475. And 500 minus 36 is 464. And I'm going to squeeze in the last one here when I get to 49, 7 squared. And that's going to be 451. So this is the expanded sum here. The first term I calculated when m was 3. This is when m was 4. This is when m was 5. This is when m was 6. And this is when m was 7. So that's how these sums work. Just getting used to the mechanics here. Eventually, you'll be asked to evaluate the series. And what that means is we want to get the quote-unquote answer. So for some of these problems, we'll just do it by brute force. And what I mean by that is we're just going to write out the sum. Well, there's only 5 numbers. It's easier just to write them out. So this is going to be 300 divided by 1, because we start at 1, plus 300 divided by 2, plus 300 divided by 3. I guess I should note here, this is going to be confusing notation here, but this time, instead of using k, we're using n as our iteration variable here. Most of the work that we do, we'll use k in that position, and we'll put n up as our top number. So I apologize for that, but just be flexible and understand the role depending on where the number is. So then I get to 4, that's 300 divided by 4, and then the last was 300 divided by 5. Now, luckily, 300 can be divisible by all these, so this is just going to be, 300 plus 150 plus 100 plus 75 plus 60, and that all adds up to 685. So when I evaluate the series, what I mean is get the answer here, and it's 685. So that's a lot of what we're going to do to begin with. Now, what you need to know is that this structure that we're practicing with has a lot of the same properties as other structures in mathematics that we've been working with. For example, our limits and our derivatives. So there are properties that go along with these. And I've got them summarized here in a table on the next slide. So let's take a look. So these are some of the important properties of our sigmas that we're going to work with. Basically, what it's letting us know is, and some of these are kind of obvious, but just like our derivatives and our limits, if our formula has a sum in it, like this one, a sub k and b sub k, we can break that into two sigmas and get those answers separately. Same thing with a difference. If we have a subtraction in there, we can break them up, do them separately, and then subtract them. Now, these last two rules are going to be very useful to us. The first one's called a constant multiple rule. And we have one of these with limits, and we have one of these with derivatives. And we're still, a little rusty with it, but the idea is if there's a factor in our formula that's just a constant, we can take it out of the sigma and do this sum and then multiply by that constant when we're done. In other words, we get the constant out of the way, we do our sum, and then we multiply it back on. And then this last rule is pretty cool. What it says is if your formula is a constant, then all you have to do is multiply the top number by the constant. Let me show you that one. That one's easy to illustrate. Let's say I want to do the sum of k equals 1 to 4 of 7. So my formula is 7. Notice there's nowhere to plug my k number in. So each time I write the term in the sequence, the first time it's a 7, the second time it's a 7, the third time it's a 7, and the fourth time it's a 7. Oops, I just wrote 4 there. The fourth time it's a 7. And then, of course, 7 plus 7 plus 7 plus 7 is 28. And so what we find is we can skip that process if we're starting at 1. And if this guy is a constant, then we could just do 4 times 7 and write 28 down. So just to drive that point home, the sigma of k equals 1 to 100 of 12 is 1200 because you do 12 times 100. We would just have 112s listed out and we'd add them up. So these rules are going to come into play here for some of the problems that we work on. Now, there are actually 3 other important rules that we're going to use when we get to the point where we need to add up an infinite number of rectangles. And so I want to derive one of them for you now, and then I'm going to give you the other 2 because it's a long talk to do those. And then I'll finish off the problems here. So this is the coolest part of the whole video coming up next. So on one of the earlier slides, we had this sum written out, which was 1 plus 2 plus 3 plus 4 plus 5. And we found out that that answer was 15. This is the sum of the first 5 natural numbers. And, in the old days, people didn't have phones to play on and things, so someone got to thinking, what would the answer be for any particular natural number? In other words, is there a fast way to add up, let's say, the first 100 natural numbers? And the way they explored that is, instead of putting a number on top, they put a variable n up here. And they said, hey, let's find out what happens. So check this out. We don't know what number n is, but we know that that series starts out like this. 1 plus 2 plus 3. And then we get bored, and there's dot, dot, dot. But we know how it ends, right? It ends with n minus 2, n minus 1, and then n, right? It goes 1, 2, 3, 4, 5, 6, blah, blah, blah. And then the last 3 numbers are 2 short of the final one, 1 short of the final one, and then the final number. And of course, you all know how to add that up, especially these 3 dots, man. We do that math all the time, right? Okay, no, we don't. The problem with this is we can't really, we don't know what to do with this, and we really don't know what to do with these either, right? So here's the trick. And of course, I didn't invent this, but I love it. What if I wrote down this same sequence? So another version of k equals 1 to n of k. But I wrote it in reverse order. So n plus n minus 1 plus n minus 2 plus dot, dot, dot plus 3 plus 2 plus 1. Addition's commutative, right? So we're allowed to switch the order. And when we do that, the trick here is to make this into an old school addition problem. And I'm just going to add straight down with column arithmetic. So first of all, let's talk about what we do when we have one of these sigma structures plus another one of these sigma structures. Well, they're the same thing, and so when you add two of the same thing together, you get two of the sigma structures. So 2 times k equals 1 to n of k, right? And then check this out. I'm just going to add straight down each term. I'm lining each term up, matching them up, and I want to see what happens, right? Okay, so when I add these first two together, guess what I get? I get n plus 1. And when I add the second two together, I get n minus 1 plus 2, which is also n plus 1. And when I add the third one together, I get 3 plus n minus 2, which is also n plus 1. And then, of course, we're not going to do anything with these dots. And then at the end, I get n minus 2 plus 3. Guess what that is? N plus 1. N minus 1 plus 2 is n plus 1. And n plus 1 is n plus 1. Okay, so here's the cool thing about this. How many n plus 1s are listed there? Well, if I count all these out, oops, that's a weird color. I hit the wrong button. If I count all these out, there's 1, 2, 3, ... blah, blah, blah. There's n of these things because we went from 1 to n. So I can simplify this by writing it as a product. 2 sigma k equals 1, that's equals 1 to n of k equals n times n plus 1. And then if I want to solve for just one of the sigmas instead of both of them, right, that's what I originally wanted to do, all I have to do is divide by 2 to get that 2 out of the way. So I'm running out of space here, but I'm going to divide by 2, cancel that one out. And then what I've come up with is the formula for adding up the first n natural numbers is n times n plus 1 over 2. So let me show you that that works for these 5 numbers. The formula is n, which is 5, times n plus 1, which is 6, divided by 2. And that's 30 over 2, which is 15, which is exactly what we got there. So the point here is we've learned that we can replace this notation, k equals 1 to n of k, with this formula that doesn't have a sigma in it. It's kind of like what we were doing when we had absolute values in our problems. When we had absolute values in our problems, we had to replace them with something else before we could do the math. It's going to work similarly with these sigmas. I can't do math with this particular sigma because I don't know what n is. But if it's the sum of 1 to n of k, I can replace it with n times n plus 1 over 2, and then I can continue my work. All right, so I'm going to summarize this on the next slide because this is a mess, and then I'm going to show you a couple more problems, and then this video needs to end. So here's that formula that we just made right here. When you see the sigma of k equals 1 to n of k, that equals n times n plus 1 over 2, and that's the one I derived. Now, we're not going to go through the same process, but the sum of the first n squares, so like 4, 9, 16, 25, 36, and so on. If you want to find out the sum of the first n squares, you use this formula here, which is n times n plus 1 times 2n plus 1 over 6. We won't go through the process of deriving that. Let's just assume somebody smart came up with that. And then there's a formula for the cubes too. K equals 1 to n of k cubed. That's n times n plus 1 over 2 quantity squared. So as we get working, whenever we see one of these, we can actually replace it with the formula and do the calculation quicker. That's the whole point. We don't have to list out all these sums. We can quickly calculate the formula. I should say compute the formula. Okay, a couple other quick examples and then we're done with this thing. So I'm supposed to add up the first 7 terms in this 300 minus k squared. And what I'm going to do is some properties to break this down and make it a little easier. So check this out. I have a minus sign here, so I'm going to break this into two sigmas. It's going to be k equals 1 to 7 of 300 minus sigma of k equals 1 to 7 of k squared. Okay, now, remember we've got a little property for a constant term, which is when you have a constant here, you could just do 7 times 300 as long as it starts at 1, and we'll get the answer for that, which is 2100. And then we have our new formula that somebody else derived for us for the sum of the first 7 squares. So instead of adding up 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49, we're just going to use the formula. The formula is n, which is 7, times n plus 1, which is 8, times 2n plus 1, which is 15, divided by 6. And when you do 2100 minus 7 times 8 times 15 divided by 6, I just crank that out of my calculator and I get 1,960. So that's the value of that sum. And I just wanted to demonstrate to you that sometimes there are faster ways to compute these sums than writing out each term. Like I did not write out the 7 300s here, and I did not write out the 7 squares here. I used our properties and our formulas to more efficiently compute this sum, which was 1960. Okay, last thing, and then I need to stop. We don't have formulas for all of the different expressions that you can come across. And in particular, if you come across an exponential like this, we don't have a formula for that. So you're going to have to do this one by brute force. So this would be 5 to the first power plus 5 to the second power plus 5 to the third power plus 5 to the fourth power plus 5 to the fifth power plus 5 to the sixth power plus 5 to the seventh, right? You got to add those up. And when you do that, I mean, I can write out what they are. This is 5 plus 25 plus 125 plus 625 plus 3,125 plus 15,625. I don't know these by heart. I already had them calculated. Plus 78,125. And then, you hit equals on your calculator. This works out to be 97,655. So every once in a while, you're still going to have to do it the old-fashioned way, right? But when you can, I want you to take advantage of our properties. Okay, work together. See if you can knock out the answers to these problems that I've posted. And then I'm crossing my fingers I'll be back tomorrow because we've got a lot of work to do here. We're getting to all the cool stuff, and I don't want to miss it. So, all right, take care, and I'll see you later.